So welcome to DC Economics. So we are going to look on how we can find the stationary point of a function. A stationary point of a function is a point where the derivative function of x is equal to 0. These are the points are called stationary because at this point the function is neither increasing nor decreasing. So the graphical, this corresponds to the points on the graph of the function of x. So when you try to sketch up the graph, you can observe that the tangent to the curve is in a horizontal line. So as the curve moves from the point to the starting point of the horizontal line, going upward, represent out the upper sides of the what is known as a local maximum. And as the way now the graph moves from the tangent, from the upper side going downward from the negative side, is where now the points represent out what is known as a local minimum, as you can observe. So there we have what is known as a local maximum, and that below of the horizontal line over there we have what is known as a local minimum. So the way the line dropping downward, going to the negative sides, goes to the side positions of a local minimum. So the stationary point of the function are the solution to the derivative change of dy over dx, which is equal to 0. As you can observe. Now, one thing we need to understand, a stationary point is called a turning point if the derivative change sign from the positive to negative or vice versa at the point. But also there are two types of turning points we are going to discuss over here. We have what is known as a local maximum and we have what is known as a local minimum. So a local maximum, these are the largest value of the function in the local region, and whereby the local minimum is the smallest value of the function in the local region, as you observe on the previous graph over there. Something to note is that all the turning points are stationary points, but not all the stationary points are turning points. So a point where the derivative of the function is 0, but the derivative does not change sign, is known as a point of inflections or saddle point. And actually, these are sometimes referred to as rising or falling. Let's come to the concept of the second derivative test. So what is concerned about the second derivative test? The second derivative test is used to determine whether a stationary point is a local maximum or minimum. So a stationary point x is classified based on whether the second derivative is positive or negative or 0. For example, under second derivative test, the second order derivative dy raised power of square y over dx square at the stationary point of x is given by this condition. If the second derivative test is greater than 0, there is a local minimum, and if it is less than 0, there is a local maximum, and if it is equal to 0, now the test may be inconclusive in one way or another. So these are the conditions that we testify concerning about the second derivative test, is where now it is used to prove out the local maximum or minimum of the function under given stationary values. So if the test is inconclusive, now we must use now some other method to determine the nature of the stationary point, such as we may apply the first order derivative test. Under the first derivative test is that we determine the nature of the stationary point at x by evaluating the sign of the first derivative point at x plus summation and x minus summations of a given value, whereby summation is less than 1, or the summation that is actually resembled given in the given specific relation. So now this determines the function is either increasing or decreasing at these points. So normally the shape of the graph may be represented in a given notified areas. If the first order derivative of the function is greater than 0 at point x or at the given stationary values, now the function is increasing at x. And if the derivative change of dy over dx is less than 0 at point x, then the function is decreasing at x. So the following table now represent out, the following solutions show out the classification of a sectional points based on the first derivative test. Suppose if we have the first order derivative of dy over dx is greater than 0 or 0 is less than 0, this will present out a local maximum. So the shape of the graph will be moving, going, resemble from the left to right hand side, going at the right hand side and actually increasing. And if the derivative of dy over dx is less than 0 or greater than 0, now that proves out a local minimum, and the shape of the graph will be going left hand side, dropping outward and then rising. So if the derivative change of dy over dx is greater than 0 or 0 is greater than 0, now this represents of the rising of inflection. So the shape of the graph will be going increasing at that side, as you can observe. And if the dy over dx is less than 0 or 0 is less than 0, now that's represent of the falling of inflection, and the shape of the graph will appear in this mode over here. So first derivative test or second derivative test is when the second derivative test is easier to calculate, that it may be easier and faster to do the second derivative test rather than the first derivative test. However, as we have seen, if the second derivative test is 0 at the stationary point, now we do not know whether it's maximum or log minimum, so we need to apply the first derivative test. So if the second derivative test is 0 at the stationary point, now this means that it has failed to determine whether the stationary point is local maximum or minimum or point of inflection. So this now will reinforce us now to apply the first derivative test to see whether the function is at local maximum or minimum at a given location of the stationary values. Let's look at an example. Find and classify the stationary point of the following function. Function of x is equal to x raised to the power 4 plus 4x cubic minus 2. Solution. We apply first the first order derivative test of the function. That will be equal to 4x minus 4 minus 1 plus 4x 3x minus 1, then minus 0. So the first order derivative test is given by the function that is 4x cubic plus 12x squared. So we equate a function of x, the first derivative is equal to 0. We solve the values of x. So when you divide over there, we factor out 4x squared, then we plug in the values of x. The stationary points of the function will be equals to 0. And another values, also the stationary values, is equal to negative 3. Now, we may ask yourself, what is the nature of these stationary points? Are they local maximum or minimum? So since we have the function of x which is equal to 0, x is equal to 0 and x is equal to negative 3, these are the stationary values. So when we equate out, we apply the second order derivative test to prove the local maximum or minimum of the function. When we plug in function of x by plugging first negative 3 inside. So when you plug in negative 3 inside, we apply first the second order derivative test on this function of x. It will be 12x squared plus 24x. So when we plug in negative 3 inside, we will obtain the function. The second order derivative test on the function on the tested first value, that is negative 3, is equal to 36. So 36 is greater than 0, and according to the condition and the stationary value, this prove out it is a local minimum, since the condition for local minimum is whereby the second order derivative test is greater than 0. So what about another stationary value, that is 0? When we plug in 0, we obtain the function, the second order derivative test of the function, and a given stationary value of 0 is equal to 0. So when we plug in 0 over there, this means that we've obtained 0. Since the answer is 0, it does not actually, this is answer tend to show out it is inconclusive, since we not determine the nature of the stationary value. So in order to testify, since this method has been failed, we apply the first order derivative test to prove out if it is a local maximum or minimum. For that case, now we take out the first order derivative of the function, that is 4x cubic plus 12x square. So under the first order derivative test, we try to plug in the values of x that is equal to 0. So when you, for example, you plug in 0 over there, you obtain the answer that is positive, that the answer will be equals to 0. But not only that, when you try to sketch out the graph and show other relevant points on the given function of 4x cubic plus 12x square, this means that we'll be having y 4x cubic plus 12x square. So here we have given values of x. We assume we have 1, 2, 3, 4, 0, 1, 2, 3, and 4. So when you plug in the value of the x function, we obtain the first bracket that is equal to 16. And when we plug in y to the function, that we plug in 2 to the equation, we obtain out the function that will be equals to, this will actually give out, will be equals to 80. And when we plug in again 3 to the function, this means that will be this will be equals to, so when you plug in 4 ln cubic plus 12 cubic square, the answer will be equals to 216. The same applies when we plug in 4, we obtain out the answer will be equals to 448. And when we plug in 0 to the function, this means that the answer will be equals to 0. And when we plug in -1 to the function of 4x cubic plus 12x square, the answer will be equals to 8. And when we plug in -2, this means that the answer will be equals to, this means that the answer will be equals to, this will give out 16. And when we plug in 3, the answer will be equals to, when we plug in -3, so the answer will be equals to 0. And when we plug in -4, the answer will be equals to, this means that we obtain out -64. So when you try to sketch out the graph, the function of x, that is the first order derivative, that is 4x cubic plus 12x square. So when you plug in function, we assume that we plug in negative sign to the function. When we plug in any value that is negative to the function, this means that the answer will be equals to positive. Now, since the answer it is positive, this means that when we plug in 0 there, we obtain the result that is 0, that is positive. So when you try to sketch out the graph will appear like this. So we are not actually going to use the property scale. So we are going to draw it roughly. That is only to show you an idea on what we actually deal with this kind of equation. So since here we have the y-axis and the x-axis. So suppose we have the y-axis and the x-axis, as you can observe. So we have 1, 2, 3, 4. We have 3, 6, 7, 8, 9, 0. And there we have 8, 16, 64, 80, and 160 up to 448. And let's assume here now we have also 8, 16, 64, 80, 160, 216, and 448. So we have this is represent of the y-axis, this is the x-axis. So when you sketch out the graph 1, 8, then 2, 16, as you go upward, the graph will go into this point over here. So when you try to sketch out the graph, remember that we had the functions, we had the given values of x and y, and we have 1, 2, 3, 4, 5. Remember we have 16, 8, 26, 0, 8, and 16, as you can observe. So when we take out 1, 6, 16, the point will be going there, 2, 8. So the graph will resemble going at these middle points, as you can observe. So our graph will appear at this shape over here. So conclusive now, the sectional point of the function. So the sectional point of the function, so the sectional point nature actually resemble that the sectional points of the function is actually increasing at the required is increasing on the left at x which is equal to 0, as you can observe. So that is how we apply the second order derivative test to prove out if the function is at local maximum or minimum. So let's look at the last example for more understanding. For example, find all the stationary points of the function of x, that is x cubic minus 3x squared minus 1, and determine whether if local maximum or minimum. The first step, we apply the first order derivative test, that will be equals to 3x 3 minus 1, 3x squared, 2 minus 1 minus 0. So the first order derivative test is equal to 3x squared minus 6x is equal to 0. So we factor out 3x outside, we find out the values of x. The values of x will be equals to 0. And also x is equal to 2. So these are called the stational values. We call them the stational points. So if we have the stational points, that is x which is equal to 0 and x which is equal to 2. Now it is possible now to prove out if it is local maximum or minimum. So in order we can prove it's local maximum or minimum, we apply first the second order derivative, that is x cubic minus 3x squared minus 1. So the first order derivative test is at that particular function is 3x squared minus 6x, and the second order derivative is 6x minus 6. So we plug in the stationary points, that is x is equal to 0 and x is which is equal to 2. The first value, that is 0, will give out negative 6, which is less than 0. So this proves what is the local maximum. And when we plug in another value of the stationary value, that is x which is equal to 2 to the function, it will give out 6 times 2 minus 6, that will be equals to 6. So 12 is greater than 0, so this proves that it is local minimum. So the total value, that is x which is equal to 0 and x which is equal to 2, prove out that there is a local maximum or minimum at these given values. So welcome to DC Economics. Don't forget to watch other videos. Bye bye.